Welcome to session 8 of data communication. We'll be looking at spread spectrum in this session. Now, spread spectrum is used to transmit either analog or digital data. Now, essential idea is to spread the information signal over a wider bandwidth. So we are employing or using spread spectrum in order to do that. It makes jamming and interception harder to use. Now, you remember that earlier on in this chapter, we are saying that mostly it's being used by the military to kind of communicate data from one point to the other. So the technique of spread spectrum is used such that the interception or the data that is going to be transferred from one point to the other, or whatever information they are sending to their counterpart, will not be intercepted. And to be able to do that in communication, we use spread spectrum. There are two types we'll be looking at: the frequency hopping and the direct sequence method. Now, the concept of spread spectrum here, input is being fed into the channel encoder, and this produces narrow bandwidth analog signal around central frequencies. Now, signals are modulated using sequence of digits. Here we are talking about using spreading codes or sequence that are typically generated by pseudo noise or pseudo random number generator. Now, this increases the bandwidth significantly, hence spread spectrum. Now, receiver uses same sequence to do demodulation of the signal, and this demodulated signal is fed into the channel decoder. So this is the block diagram of the spread spectrum. So we have the input data coming into the channel encoder, then the data is being modulated, goes through the channel. Of course, we have the demodulator, then the channel decoder, then we have the output. Now, at the modulator and the demodulator section, that is where we have the spreading code, which we are calling the pseudo noise or pseudo random generator. So you can see both of them being used at the modulator and the demodulator session. Now, spread spectrum gains. Now, immunity from various noise and multipath distortion is being employed, including jamming. Now, this can hide or encrypt signals. Here, only receiver who knows the spreading code can retrieve the signal. Once you don't have the pseudo-random code, you are not able to decipher what information is being sent across the network. Now, here, several users can share same higher bandwidth with little interference. We are talking about cellular telephones, we are talking about code division multiplexing, then code division multiple access, CDMA, which we'll speak about in our next session. Now let's look at the pseudo-random code. This is being generated by an algorithm with an initial seed. Okay, so the initial seed can be a number made up of binary zeros and ones, and these numbers are being generated using an algorithm. We have the deterministic algorithm, which is not actually random. Now, if the algorithm is good, then the results pass reasonable test of randomness, or whatever data you are trying to pass through the network is able to give it that pass status. Now, there's a need to know the algorithm and the seed to be able to predict the sequence. Knowing the algorithm without a seed does not guarantee you of intercepting the data. So one needs to know which algorithm was used and the initial seed. That is only when one can know what kind of data was sent across the network. Now let's look at the frequency hopping spread spectrum. Now here the signal is broadcasted over seemingly random series of frequencies. Of course, we said that those frequencies are called the carrier frequencies. Now the receiver hops between frequencies in synchronization with the transmitter. Now, those who eavesdrop on the network, they hear only intangible blips. Whatever information they get through that is kind of like a noise to them. It doesn't make meaning to them. Now, jamming on one frequency affects only a few bits with respect to the frequency hopping spread spectrum. So typically, 2 raised to the power k carrier frequencies are used, and this generates 2 raised to the power k channels. So if I have 2 raised to the power 2 carrier frequencies, I'm expecting to get 4 channels. Now, the channel spacing corresponds with bandwidth of the input signal. Each signal is being used for fixed interval. So we have 300 milliseconds by the IEEE standard with regards to wireless, and some number of bits transmitted using some encoding scheme. It may be a fraction of bits that can be used. Now, the sequence are dictated by spreading code, as we saw earlier on. Then we have the direct sequence spread spectrum. Now here, each bit in the original signal is represented by multiple bits in the transmitted signal using a spreading code. Here, the spreading code spreads signal across even wider frequency band in proportion to the number of bits being used. So a 10-bit spreading code spreads signal across 10 times the bandwidth of just 1-bit code. So you can imagine. Now, one of the methods being employed by direct sequence spread spectrum is the first combining the input with spreading code using XOR operation. I guess you remember your digital logic with XOR operation. Input bit 1 is inverted spreading bit code bits. Then input 0 bit doesn't alter the spreading code bits. Now you will find examples of these in your lecture slides. Now the data rate is equal to the original spreading code as far as DSS is concerned. Now let's look at code division multiple access, CDMA. This is a multiplexing technique used together with spread spectrum. Let's assume we start with a signal data rate of D, which we are calling the bit data rate. Now we break each bit into a number of chips. We can say K chips according to some fixed pattern specified by each user. So each user has a user code based on the K number of chips that was generated. It means that our new channel has K times D chips per second to handle. Let's consider A communicating with base. Now base knows A's code. So assume a communication already is being synchronized between them. Now A wants to send a 1. So A will send a chip pattern, say 1, 1, negative 1, negative 1, 1, negative 1, 1. That's A's code. Now if A wants to send 0, A will invert this code. So we get, instead of 1, we'll get negative 1. Instead of negative 1, we'll get a 1. And that's the complement of A's code. Now the decoder ignores other sources when using A's code to decode. And this we are calling the orthogonal code. This ends the session. I'll see us in the next session.